Hi everyone, so we're continuing on from the lecture notes that we left off the week before reading week, and the last thing we were covering was the reactions that alkynes can undergo, and the very last one that we have not yet spoken about is the acid catalyzed addition of water to propyne. So we're going to just navigate through those steps, and for the most part it's very similar to what we've already encountered. There is one small new part at the very end, but we're going to take it step by step together. So the first thing, as always, is can you draw propyne? So I have my little pen here. Prop tells me I have 3 carbons in a row, and yne tells me I have a triple bond. I'm not given a number, and it wouldn't really matter in the structure, so you can just draw your double or your triple bond between any of these carbons here. Okay, so remember, when the number isn't given, we can assume it's between carbon number 1 and 2. And in this molecule, it doesn't matter because I can draw from right to left or left to right, and it's all carbon number 1 here. So I need to make sure all my carbons now have 4 bonds. So this one needs a hydrogen, this one in the middle has 4 bonds, and the last one here needs 3 hydrogens. So this is propyne. Now I'm only really interested in this carbon and this carbon, so I'm going to summarize everything else around it to make it simpler for myself. Okay, so this really can also look like this: C triple bond C with a H, and that big CH3 group can just become a nice little neat compact CH3 group. Within that molecule I have 2 pi bonds and a sigma bond. We know those 2 pi bonds have electrons that are available for reaction. Remember that this is an acid catalyzed reaction, so I must also have a H plus or a proton floating around. So I'm going to say the reaction can proceed forward with a H plus. So I am now going to show the movement of electrons from my pi electrons to the hydrogen. So I break one of those bonds in the middle here. Okay, so again between my red carbon and my blue carbon. So I go from a triple bond to a double bond, and I add the hydrogen to one of the carbons only. And this is where we need to think of our carbocations. We have 2 possible places to add them. This is where you can use your Markovnikov's rule. So Markovnikov states that we must add the hydrogen to the carbon that already has the most hydrogens. So just while we're getting used to things, I'm going to draw out both possible carbocations, and we're going to identify which one is most stable based on Markovnikov's and based on the increasing stability of a carbocation based on its neighbouring carbons. So I can have 2 possibilities. I can have, I can add, maybe we will say this hydrogen here. Maybe I add it here. And I keep this one as it was, so it means this carbon here, my blue carbon on the right, that gets a positive charge because it's a carbon with only 3 bonds and it now has a positive charge. It's a carbocation. I can have that as an option, or I could keep the red carbon the exact same as it was, and I could add my new hydrogen to my blue carbon. So this is my new hydrogen. So which one is most stable? So I suppose first note now, my red carbon is my carbocation because it has 3 bonds and it now has a positive charge. So Markovnikov's rule said add the hydrogen to the carbon that already had the most. So based on that, I mean the most hydrogen, so based on that it's the blue, isn't it? We should be adding it to the blue one here. And if I add the hydrogen to this blue carbon, then my red carbon becomes my carbocation. And let's just see how many carbons are surrounding it. So we have 1 neighbouring carbon and 2. So that makes that a secondary carbocation. On this one, if our carbocation is this blue one here, let's look at how many immediately neighbouring carbons it has. Well, it's only bound to 1 immediately, so that makes it a primary carbocation. And we know that secondary carbocations are more stable because the surrounding, those immediate neighbours, those next door neighbour carbons, help counteract that positive charge. So this one is our most stable. And that's the one that goes forward in the reaction. Okay, so I'm going to now redraw that down here. And again, just keep up with the colour coding. So now we're going to do what we actually intended to do, which is add water. So, whoops. So I have oxygen with hydrogens. So remember, oxygen, assuming it doesn't have any formal negative or positive charge, will always have 2 bonds and 2 lone pairs of electrons. So 4 electrons total available for bonding. So I'm going to show I have a source of electrons here with my oxygen. Okay, so that is my nucleophile, and I have an electrophile here, this carbocation, this red carbon with a positive charge. Don't want to get rid of that positive charge. So I'm going to show the movement of electrons from the source to the positive charge. And when I do that, I get this guy here. I've added the full water molecule. And the first thing that sticks out is, well, that oxygen can't currently be happy because it has 3 bonds when it only wants 2. It's actually after losing 2 of its electrons here, because remember, this carbon had a positive charge. It had no electron to share to form that covalent bond, so oxygen gave both of them. Okay, so now oxygen currently has a positive charge because it's down 2 electrons, okay, or down an electron, I suppose. So now we move on to the next step, okay, which is getting rid of one of these hydrogens, isn't it? Because oxygen wants to only have 2 bonds. So what can help us? Well, remember, we are in an acidic solution. We also deprotonated an acid earlier, okay? So remember, very early on, we took a proton away from an acid. That deprotonated acid may still be floating around. So you can say your acid, maybe acid minus, I don't mind what way you kind of present it, is going to say, well, I'll take that proton back. And the hydrogen say, well, as I'm going on my way, I'll give those electrons back to oxygen that I borrowed earlier. And we'll end up with a molecule that looks like this. And this is a new one for us. We've never encountered a molecule like this before. And oxygen got its 2 sets of electrons back. So we have a molecule with a double bond and with an OH group. So this is an enol. En coming from that alkene, that double bond, and that ol coming from the alcohol group. So it's an enol. Now, in this structure, in this configuration, it's not super stable. It doesn't really like staying like this, okay? So it's going to start to try and rearrange itself to make itself a little bit more comfortable. So what we're doing over the next few steps is just showing how it makes itself more comfortable, how it makes itself more stable. So again, I'm going to now just redraw that enol down here, and this is the new part. This is something we haven't encountered before. Okay, so why is it uncomfortable? It's uncomfortable because given the choice, it would much prefer to have a C double bond O than a C double bond C. The C double bond O is just more stable, more secure. So if we can get that, it will. Is there anything floating around to help it do that? Yeah, we still have acids. Acids are still floating around. We also have a pi bond here, which is still available for reaction. So, very similar to what we've dealt with so far. We're going to say movement of this last pi bond to form a bond with a hydrogen. And we're going to just go directly to our Markovnikov's rule. We're not going to draw out both carbocations. You can if you like, but just, I suppose, to save on the how complex it is. We're just going to say we are going to add this new hydrogen to the carbon that already has the most hydrogens. And we already see that it's this blue carbon over here, isn't it? That blue carbon has the most hydrogens, so we're going to add our new hydrogen to that one. If we do that, we now have this carbon is happy, so our blue carbon is happy. Our red carbon not so much, because now it only has 3 bonds. It gets that positive charge, it's carbocation. So this is where the oxygen sees its chance, sees its opportunity. So a carbon can be positively charged, but so can the oxygen. We can move those electrons. So the oxygen might say, I'm going to take advantage of this, and I'm going to actually give 2 of my electrons here to that carbon. So I'm going to form a bond with it. And this is a step that goes back and forth, back and forth, back and forth, okay? So it's an intermediate, it's happening very, very quickly. So we're going to show it in square brackets, and we're going to show these two things can flip back and forth and back and forth, okay? It's not stagnant. And so if oxygen gives that, gives those lone pairs, we can end up with everything here so far is staying the same. If electrons are moving from this oxygen to this carbon, it is forming a bond. So it's forming this double bond, okay? And that hydrogen still remains the same. So remember, it's these electrons it said here. I'm going to share those with you for a moment. You had a positive charge, I'm going to share those. So now, carbon's positive charge is gone, but oxygen has given two of its electrons to form that bond. So it now has a positive charge. So it's still not super happy, but it's closer to where it wants to be. And is there anything that can help us get rid of this hydrogen? Well, yeah, we have loads of deprotonated acids still floating around. Some resources might also show that you can use water. Water as a base. Water will take an electron, or sorry, will take a proton. So depending on what you're using to study, you can see either or, and I'm absolutely fine with you presenting either or. Either your deprotonated acid, because it's an acid catalyzed reaction, or your water floating around. I'm absolutely fine with either of those. So I'm just going to stick with my acid, just because I started with that already. I'm going to say, well, this is going to pick up this hydrogen. So it's forming a bond with hydrogen, and the hydrogen is going to give its electrons back to oxygen. And when it does that, and I suppose what I should also show you is this rearrangement part can go back and forth depending, okay? Going back and forth, I mean, is in direction can go forward or it can go backwards. So that's what we're showing here. So a few different arrows. This arrow here saying direction is only proceeding forward. This reaction says it can go backwards and forwards. And this one is saying you have this intermediate that's flipping, okay? So one bond is flipping back and forth, back and forth. So just so you're aware what those arrows mean. So moving on to our next step to show what we actually generated there. So remember, it can go back and forth. We've added the acid to this hydrogen, and hydrogen has broken its bond here. So we're just showing our product now, what we're actually left with. So we had carbon, single bond. I have my CH3 up here. This is also a CH3, isn't it, really? So if you want to summarise that CH3, that's absolutely fine. We broke the bond between hydrogen, but we maintained that double bond. Okay, and oxygen has now got its two lone pairs of electrons back. This really is, and we can simplify it, it's the same thing as saying CH3, CH3. And this is our molecule. And if you look closely, you can see it's a ketone. Okay, so this is a ketone. More specifically, it's 2-propanone. Okay, so we have a ketone because we have this double bond O in the middle of the structure, okay, between two OR groups. It's on carbon number 2. Okay, and we have 3 carbons in the structure, so it's propanone. And this ketone is the most stable, okay, the most stable configuration. So we're going from this enol to this ketone because this is what was going to make it the most stable. So when you have these ketones and these enols, and they can kind of flip back and forth between one another, because really, if we just summarize it here, our initial enol looked like this. I'll just try and make that a little bit neater. So this was our initial enol, and this is our new ketone. CH3. So really, all that has changed is, bar this addition of a hydrogen, but really the main thing has changed is you've gone from the double bond here to your double bond here. So you've had the movement of electrons slipping back and forth there. And when you have that, they become known as tautomers. And tautomers exist in equilibrium. So again, you have roughly the same amount of them. They're flipping back and forth, and they're interchangeable. By the movement or migration of one atom or group of atoms within a molecule. So that's what we're dealing with here. And as I said, this is only happening to make the molecule as stable as possible. The molecule will know what it wants, it knows what requires the least energy, and in this case, the C double bond O bond is far more energy favourable, far more stable than the carbon double bond carbon, and that's why we're doing that. So that is the final reaction mechanism. Let me zoom out a little bit here to show the whole thing. So that is the final reaction mechanism for your alkynes, and it is a little bit different, okay, and it does require I suppose a little bit of knowledge for that second part, for that rearrangement, okay, so just be conscious of that. So I suppose we can really divide it into two parts, can't we? We can go from here, part 1, which we're very used to, and here to part 2, and this is that rearrangement. This is the new part. Okay, so take your time to get your head around it. And of course, if you do have any questions, you're more than welcome to ask in class or email or whatever you need to. So give that a go yourself. So attempt it in your notes and just see how you get on.